Keynote speaker, Mr. Ted Hurewitz, about to start. He's going to discuss RCA computers in the 1950s, and he was there working on them. I give the floor to Ted Hurewitz.
Hey, thank you. It's getting away from me. Okay, can you hear me? Do I need to project? How are you guys sitting behind the poles? Oh, limited vision seats, just like we used to have at the ballpark in Philadelphia. Limited vision seats to see the Philadelphia Athletics. Okay, my name is Ted, as you know. You can always call me Ted. No honorifics where I come from. What I'm going to do today is try to put you in the time capsule, take you back to where I was way back when, just coming into the computer business as a kid. My background was in accounting, believe it or not. I didn't know the first diddly about engineering, not at all. But when I was at the Wharton School studying accounting, one of the things I did was a senior paper, and that senior paper had to do with punch card accounting. At the advice of a CPA whom I knew, he said, you should look into punch card accounting, Ted, while you're at school. I did that, and that little paper got me into RCA, a job as a programmer on a project called Bizmac. Some of you might know. Bizmac stood for, the acronym was Business Automatic Computing. Everybody had an ACK, automatic computing at the end of the like UNIVAC and so on, Universal Automatic Computing. Well, we were Bizmac. Bizmac at the time I joined was an engineering group with a very, very small number of programmers for an activity of that nature, maybe a handful, 6 or 7 of us. The professionals, the ACE professionals, were people who had 6 months of experience. These were the old hands. I came in as a kid knowing nothing, but I soon found out a company started by David Sarnoff and others, spinning out of General Electric. Everybody knows who David Sarnoff is, I assume. He got his first public fame, I suppose, as the radio operator who was handling communications with the rescue of the Titanic survivors. He was receiving signals at the top of the Wanamaker building in Philadelphia at the time. And his career is just legend. He was the founder and head of RCA and the active head of RCA. When I came in, I found out what the corporate culture was. Very interesting. And you should know this if you're going to go to work for a company. What's the culture? Every company has a culture. Here was RCA's pronounced culture. We are the company that derives 80% of its revenue from products that were not in existence 10 years ago. That was it. Now, what did that mean? It meant that we were an innovative company. We're a company that is at the leading edge in new product development. And that's what it said to me. I don't know, what does it say to you? If they had maintained that culture, in my view, they'd still be around. They'd be leaders. But somehow along the line, as you'll soon find out from me, that sort of thing somehow faded out into the background and people forgot their culture. And when you forget their culture, you're not meeting the challenge of history. And what happens to organisms that don't adapt to changes in history? They become extinct. Did I make a point? Okay. However, in the early days, the corporate culture was new is good. Let's make progress. Okay. What else do we need to know? You don't mind if I refer? Another thing about RCA that you should know is this, that there was a very strong connection between Radio Corporation and the government, particularly the military. You probably know that David Sarnoff was a brigadier general in the Army, and there are a number of other executives who had high military positions. We, as a division, were headed up by a rear admiral who retired, a gentleman whose name was Dorsey Foster, and following him, another admiral, fighting admiral, naval air guy, Raoul Waller, who commanded a carrier during World War II. So we had a strong military connection. Now I mentioned this because the government had a lot to do with what happened in the computer industry, as you all know, particularly at RCA. The government was interested in computers for many reasons. One of them was that we were in a Cold War, and we needed better tools, better instruments for handling logistics than was available with punch card accounting. Punch cards were way too slow to handle logistics in the Korean conflict. The conflict was called a police action? No. The conflict was a war. We were in a war. And I'm sure you've all seen some of these early episodes of MASH, where the mosquito netting arrives in the winter and the blankets come in the summer. You know. That was literal. That was actually happening, and it was scary. The government said, we're going to invest some money in some better data processing tools. We think maybe computers might hold the answer for us. And so the government funded computer developments around the globe, and America was the leader in computer technology in those days and maintained that leadership for quite a long while because of government interest. Okay, next thing I need you to know is the goods and bads of RCA's participation, the generalities before I get to specifics. RCA, it turns out, was a terrific company from the standpoint of developing electronics. By the same token, they get sort of a C- in my book with respect to developing mechanical stuff. So they were way behind in the mechanical side, but way ahead in electronics. Now, how did that reflect itself? Well, if you think about what goes into a major computer today, you can think about the part that's electronic. Oh yeah, we've got the motherboard and the logic and all that stuff. But we also have a hard drive. And we have other drives for memory. And we were way behind it at the beginning. Starting way behind the line. Our mechanical engineers didn't like the notion that they were lacking, but that was the case. That was the fact. So here comes Ted off the street, hired almost by accident to become a programmer in an area where the ultimate goal was to establish computers in business, and they needed people with business backgrounds who knew a little something about data processing to join that group. Eventually, we're going to make a computer that will sell into businesses. We all know that the original computers, the ENIACs of the world and the UNIVACs and so on, were for computational work. You all know where ENIAC went, isn't that right? Aberdeen Proving Grounds, and its mission was to calculate trajectories for artillery shells. Okay, but eventually we thought that we would use computers not for computational work, but for moving data and processing data. Okay. That's why Ted joined that group. That's why RCA saw fit to take me in. My introduction was, here you go, Ted, here's your desk. This is the group you work with. This is an engineering group. We're building a prototype to a mainframe. We call this our breadboard. That was the breadboard for Bizmac. And we want you here to write programs. This will be your training ground. We want you to write programs. So what's a program? Is there a book? No. No book, no programming manuals.
Ted, what year is this?
1953.
Okay, thanks.
This was,
that framework.
my intro to RCA was March 31st, 1953. No books, no teachers.
No compilers.
No, compilers. Whoa, wait, I didn't even get to that yet.
Did they say what the program should do?
No? Oh, yeah, they did. They did. That was the one thing they did tell me. We want you to write programs to help the engineers test our equipment. We want you to try to write a program that will stop and start a tape unit at different frequencies, since we want to see if we can make it, shake it apart. Check the componentry, shake it apart, make it fail. These are test and diagnostic routines that were required. So, okay, well, what's a program? A program is a list of instructions that the computer follows to do something. Well, what's an instruction? I remember coming home from my first day at work and telling my dad, who was a dentist, "Hey, Dad, I finally got a job after college. I'm a programmer." He says, "What time does your program come on?" You know? That was true. It's true. It wasn't a joke. He meant it. And I finally told him, you know, "Oh, it's not that kind of thing." He said, "Do you get paid?" I said, "Sure do." He said, "Well, that's okay then. It's all right. As long as you get paid. It's not a hobby. It's not one of those things you do for fun." "This isn't fun, Dad." Okay. Well, at work, I came into work and I was assigned to an engineer, and "What does a program serve?" And he said, "Don't call me sir, I'm younger than you are." I was 23, I think he was 22. The oldest person in the whole team, the team manager, was 26 years old. And this was a fairly substantial group of people. 26 years old. That's it. We had no old timers. There weren't any old people in the business. We were all young. He said, "All right, I'll show you how, this is an instruction." Okay. Our logic was laid out in the form of blueprints, and the walls were papered with logic diagrams. So he took a highliner, and he said, "This is where we start an addition, an add instruction. It starts here, and it goes through this gate and that gate, and we close this when that happens, and open this when that happens." And he took me through the logic. My head was spinning, and this was only one instruction. It took 6 months before I finally got it. I had an epiphany. I woke up one day and I said, "Oh man, this is how it works. Ah, great, okay, I got it. Now I can maybe do some stuff." So I went to my boss and said, "Boss, how about if I write a book, a little manual, so everybody doesn't have to go through what I just went through? I'll try to document this stuff, and we'll have a programming manual." He said, "Good idea." You know, everything you suggested was a good idea. I wound up writing a programming manual. Okay, so let me tell you about the breadboard. Well, you're going to love this. I know some of you guys would really be challenged. You'd have fun with this stuff. Firstly, there were no assemblers. There were no compilers. Programming was done in binary, except we used a shorthand notation. We used octal. An octal digit, as you know, represents 3 binary positions, right? 8 possibilities. The coding for data was 6 binary digits. We didn't have the notion of 8 bits per byte. That notion didn't happen until later. 6 digits represented a character. Why would you need more than 64 possibilities? We have 10 numbers and 26 letters. That's only 36. Oh, man, spare me. But that's what we used. Everybody else in the world had computers with fixed word lengths. Right? Fixed word lengths. You all know that? Not us. We weren't that stupid. We used variable word length, and we used a symbol to represent the beginning of a word. A word meaning field in these days. We had a start word symbol, and we had a start record symbol and an end record symbol. 3 special symbols devoted to controlling data. Okay, having said, now let me give you the technical background and what we were looking at with the first Bizmac prototype.
You had the idea of a record.
Say?
You had the idea.
We had the idea of a record. Yes, we did, and a file.
You had the idea of a record.
And the file symbol, too. I forgot that one. And a record and the file. Yep. We did have that idea. Okay, let's look at the guts. The RAM was made of Radicon tubes. We used a RAM that was 1024. Not 1024K or 1024 meg. 1024 character positions was the size of our RAM. But wait, it gets even better. It was split into two banks, upper and lower bank. And if you wanted to perform an arithmetic operation on two pieces of data, they'd have to be in back-to-back locations in the banks. One in upper and one in lower, but in corresponding addresses. Can you picture this? Okay. We had maps, which were long pieces of paper, because addressing was literal. There were no data names. We had to know the exact memory location of every piece of data we were working on and map it out on paper. Okay. And we were dealing in, of course, octal, base 8. It got to be so ingrained in my thinking that when I was writing my checkbook, I forgot to write 8s and 9s. You know, I went 0 through 7, and my wife said, "What are you doing this for? You should have been number 8. I said, "There are no 8s. 8 doesn't exist."
8 equals 1.
Okay. Actually, it was n minus 1, because all zeros represent, you know, we used all 1s to represent 8. N minus 1. Okay? All right. Yeah. The mass memory was tape, serial. We had no drums, we had no discs, we had tape, but it wasn't even reel to reel. Our tape units were pieces of tape and 2 bins. Each side of the bin had a scale. And when you flop the tape over and you got too much tape on this side, the scale would say you're at the end of tape. Oh, yeah. Can you picture this? There was no punch card input and no video console. The consoles are pretty much like what you have out in the exhibit hall and some of these old guys, switches and lamps. The console for the Bizmac was so large that you could stretch out on the desk and fall asleep on it. I mean, it was just like, you needed a roll, you needed a chair on wheels. Just to set switches so that you can start something. There was no operating system, none. Everything had to be done manually, everything. Okay, so how did you ever get anything done with that kind of configuration? We did. And guess what? It was really fun. I saw one of your guys out in the exhibit hall who just showed me he wrote a program in hexadecimal. And it was running, and it was really nice. He had a little image. It took him all night to do it, but it was fun for him, and it was fun for us too. After you get the hang of it and you can get it going, the first time I ever ran a program on that prototype and saw it work, it was a high. I never needed drugs or booze after that. I had a high, and I was in love with the computer business. It was a romance that's lasted for 56 years. Yep.
Pardon me, when they built the thing, though, didn't some engineers test out these commands to build some commands physically into the machine?
Oh, yeah, they did.
So they had run those things.
Oh, yeah, they had.
And they had never put them together in an extended program.
That's correct. And they never really used the programs to check the peripherals. We were checking the peripheral gear, trying to make the peripheral gear fail. That's really what we were doing.
So it was really an engineering application.
It was really an engineering application. Yeah, the first application was an engineering application. Exactly right. Having said, let's see, what else? If you wanted to key in a program, you keyed it into paper tape. We did have a paper tape reader. That was pretty good. That was automatic. When it worked. And if you wanted to edit your program, you could edit it on paper tape with the scissors and some sticky tape. Cut and paste. Exactly right. Question?
Why didn't they use punch cards? Because that was an existing technology.
We know. I don't know. That did come, but it came in the commercial version of Bizmac.
That's
It
what
was
we
all
do.
hand. These were the guys that were innovative.
Yeah, but they already had punch cards, so why?
Punch cards existed since 1890.
Yeah.
So
So
that
that an
would-
IBM technology that they couldn't break into?
No, they just saw fit to do punch paper tape.
Okay.
Okay. Later, of course, with the commercial versions of Bizmac, and there was a commercial version of this guy, here's what happened. Technology advanced. The Radicon memory disappeared, tube memory disappeared, because Jan Reichman and company at Princeton developed core memories. These were matrices of cores with 3 wires inserted in each core. It's a solid state memory, and so we were able to go immediately from 1024 memory to 4096 and larger. We forgot the opposite bank stuff. It was all one contiguous memory. We didn't have to have data placed any place special to work on it. We went from floppy tape as our mass memory to a drum. We still had permanently connected reel-to-reel tapes for large mass storage. And so the first installation that was made at the Ordnance Tank and Automotive Command in Detroit for handling of inventory, worldwide parts inventory for vehicles. That was the very first one. That installation was the size of 2 football fields, and most of that was taken up by tape units, which were permanently connected. They had no concept of removable tapes. The connection between tape units and machine trunks was handled by telephone switching, and they bought a telephone switch from North Electric that was adequate to handle telephone traffic for a town of 10,000 people. And that was delivered, actually delivered and installed in Detroit. Of course, we were still using vacuum tube logic. And so, you know about vacuum tube logic, it generates heat, and heat is the enemy of electronics. We all know that, right? We have to keep it cool. So 2 26-ton precipitrons were installed, feeding cold air into the racks. And, you know, the racks were literally like lockers at a locker room at the golf club. Rows of racks with no doors, just electronics installed, and vents to the air conditioners, feeding cold air in. In Detroit, it didn't really matter because in the wintertime especially, you know, if the air conditioner failed, just open the windows. It was cool enough to keep things going. So this was Bizmac. Not very many were installed, but a few were. This is the 50s. In 1954, I attended a seminar at Massachusetts Institute of Technology on a field called automatic programming. At that time, a number of papers were presented, different proposals, how to get us out of this fix of having to write machine code. This is 1954. And the most brilliant paper I heard was presented by a lady whose name is Grace Murray Hopper. Is that name familiar to anybody?
Oh, yes.
You know who Grace is? She was at UNIVAC at the time. Well, she started with Howard Aiken up at Harvard on his electromechanical system, and then moved to UNIVAC with Eckert and Walkley. And she was their chief programmer, I guess. That was her title. She presented a paper that said, in effect, we can develop an artificial language. We can write statements in that artificial language and process those just like they were data and create a corresponding set of machine code in binary. So now we have this notion of source code and object code. And you know, there were a lot of other contributors. There was John Sabakis at IBM and a bunch of other people who were involved in this, but I credit Grace with the notion, with the seminal notion of artificial languages, pseudo-language for writing code, source code, and the notion of compilation. And she didn't have a notion of compilers or higher level languages. At the beginning, that was not her forte. But she did say, I can develop an assembly system where if I want to write an add command, I write the word ADD. And if I want to write a subtract command, I write the word SUB, and that gets converted to the equivalent for that system. Oh, lovely. Everybody went home from that and began to write assemblers. Now that was really nice. And what it did was it improved the productivity of programming about an order of magnitude overnight. You see, in machine code, we could average about 10 instructions a day if you're a really good programmer. With, yeah, about right. Does that go against what you know? Can you do better than that? We couldn't.
Well, no, not in.
That was true.
Not in binary. I couldn't write one instruction in binary.
Well, the really good people could write about 10 instructions a day.
The concept of well-ordered sequence of ones and zeros, that throws me right there.
Okay. There was another notion that also went by the boards. When we were writing the original code, we had very limited physical capacities. And so what we try to do is we try to write programs that maximize the use of circuitry and minimize the amount of storage that was required. And the code tended to look like spaghetti. I mean, it was not a structured format for writing code. So the problem was that if you wrote a program and didn't see it for 6 months and then came back and had to maintain it, you forgot what you did. Well, yeah, you did. And it was really difficult to get back into the logic. So that notion didn't come around for a little while. And boy, programming was really a mess. There was a huge demand for programming and not very much supply in those days. So here comes Grace. She improves productivity almost overnight by an order of magnitude. Now we can average about 100 instructions a day using an assembly language, which is really great. Okay, now remember what I said to you earlier. The government funded a lot of the development of computers, and because they were so concerned with logistics during the Korean conflict. So what happened was there were installations all over the map of different computers. Computer brand A was at Fort Monmouth, and brand B was at Picatinny Arsenal, and brand C and brand Z, and scattered all over the military landscape. Now, why does that turn out to be a problem? Because the languages were machine-specific. There was no portability. So if you knew GE's Jovial system, it was good if you were on a GE system, but those programs wouldn't run on anybody else's system. And if you knew that language, you weren't going to write programs in anybody else's system until you learned the language. And you had to retrain people. Which language do you know? Which language do you know? Okay, we'll have to learn this new one for this system, and you couldn't move people around. This lack of portability of both programs and people led to another development government-sponsored. And that was the third generation of language. First generation being machine code, second generation being assemblers, the third generation being higher level languages, compilers. So what happened in reality was the government picked a person out of the Department of Standards. His name was Charlie Phillips. Does that name ring a bell with anybody? Charlie headed up a joint industry government council. And he said to the industry, you will co-join with me or you've seen your last dime of government business. And at that time, the government was about 80% of the total computer market. You know the 80-20 rule? You get 80% of your business from 20% of your customers. Well, the government was one of the 20% that gave companies a huge amount of revenue. Everybody joined that council, including RCA. I appointed one of my, by then we had about 200 programmers and I was running it. I appointed one of my guys to be that when that council.
What year are we at now?
We're in 56. The result of those meetings was COBOL. The person I appointed got some real fame, and I didn't get much fame, but he did. His name was Howard Bromberg, and Howie Bromberg became an editor of Datamation magazine. Have you ever seen any issues of Datamation?
Yeah.
You might see his name on the masthead. Howard Bromberg was my representative. What happened here was we agreed on a common language. COBOL stands for Common Business Oriented Language. That's COBOL. Everybody agreed on that standard. And then we were given a mission. Go home and write a compiler for this language. And now we've solved the problem of portability, right? Sure. If you do COBOL, you could write a program here or write a program there. It didn't matter what brand system. If you wrote a program for brand A, you could just simply recompile it and it would run on brand Y or Z. All you had to do was recompile it. And that was very good. It took us out of this problem of language that would be particular to a brand. Suddenly that disappeared. And now we got the notion of industry cooperation in standards. Hey, guess what? Industry cooperation in standards, what does that remind you of? Well, antitrust, but how about the internet? How does the internet exist unless there's cooperation on the part of everybody to obey the standards for communication? Like HTTP and HTML and HTTP and other standards. Agreement from a community that was competing with each other for business. But we had to agree on standards. And this was the notion. Okay, so here we go. We're now into advances in the state of the art. Oh, man. You all know Moore's Law? Everybody knows Moore's Law? For those of you who may not be familiar with it, Moore's Law is really not a law, it's an observation. It says that every 18 months, the processing power of computers approximately doubles. Another way to say that is we get maybe twice as many components on a chip in these days as we had 18 months ago. About every 18 months. And the notion then at the beginning when we first heard this was, where does it end? You know, where does it end? There has to be an end someplace. And that was 45 years ago, 40 years ago. Moore's Law is still working, isn't it?
Sort of.
Isn't that right? Sort of. Sort of. But it was a pretty cool observation for its time.
It was.
Okay. So Moore's Law kicked in, and now we have RCA's Components Division developing circuits that use Bell Labs transistors and resistors. And now we have integrated circuits, right, on boards. And then we get another government influence on the design of computers, and that's called NASA. NASA wanted a computer small enough and light enough to fit into a space vehicle and be effective. And so they urged industry to miniaturize. Let's make stuff smaller and lighter and more reliable and less power consumption. The NASA influence. So industry complied, and we went from large-scale integrated circuits to very large-scale integrated circuits in a pretty short amount of time. We went from the primitive drum memories that we had to disk memories. We had a company named Winchester who came up with a disk that was encapsulated in a metal can, a little container to keep air pollutants away from the heads on the disk. Right? Everybody knows about that, Winchester technology. And that's still with us, is it not? Has anything replaced Winchester technology for hard drives?
SSD. Solid state.
Solid state stuff, yeah, flash drives, right. Yeah, okay. But in those days, we didn't have flash drives. I have one of those. We all have one of those.
But rotating memory is certainly
Rotating memory, yeah, Winchester's still pretty good for rotating memory. So now we were able to miniaturize. We had much better, much larger mass memories. The tape units disappeared. We didn't need tapes for anything anymore because we had removable and replaceable memory objects like floppy disks. Originally, the floppy disk was what, a 5-inch floppy? 8-inch floppy, yeah. And we went to a 3.5-inch, and now we're down to the flash drives. But okay, so here we go. We're moving away from Bizmac. There are a limited number of installations that could handle anything as large or as kludgy as Bizmac. Few of them were delivered. So we start this new development at RCA. New design effort. New design effort, we're going to design a whole new computer using all this slick technology.
So all this time, it's been on essentially the same hardware?
What
from
time?
53 to... From
53 to 56, we started a design project in 56.
Okay.
The design project had to do with the RCA 501. It was called the 501. Now, here's what happened, actually. The engineering team, which is at that time headed by a guy named Arnold Spielberg, does that name ring a bell?
He makes movies?
His son, Stevie. I call him Stevie because I saw him in feet pajamas. I was over at Arnold's house for Christmas dinner one year, and here's little Stevie running around with feet pajamas. You know, hey, Stevie, keep your flap shut. But look what happened to him. He's a great guy. His father was a great guy and a good engineer and a good leader. His father came along to me and said, hey, Ted, we want you on the design team for the 501. And I said, why? He said, because you've made so much noise about how rotten the Bizmac was structured, we don't want to hear that again. So you're it. You and a couple of other guys who work with you are going to be our guys to design the order code for the 501. And that was our new assignment. We worked with the design of the order code for the 501. These are the instructions. This is the instruction set we want this to have, the machine instruction set we want this to have. And here's how we want it to work. And we went through that logic, I guess, for maybe a year, year and a half. And finally, we got a prototype. We got the 501 built. And boy, compared to what we had seen before, it was a dream. It was a dream machine. It had a video console, no more switch setting and lamps. Didn't have to read anything in binary. It had a keyboard for input. Whoa, a real keyboard for input. We didn't have to set switches. This was pretty nice. By then, we were into the 8-bit set, the 8-bit representation of data, the byte, and probably everybody in this room knows what byte means. Do you know what byte means, where it comes from? Binary yoke transfer element. Did you know that? Yeah. That phraseology came from IBM's Federal Systems Division up in New York. I forget the town. Where was their Federal Systems Division? Anybody know that? Kingston. Kingston, yeah, Kingston. That's where that came from. So now we have an 8-bit byte, and guess what? The world's standardized on code. Oh, great, we have a standard code. It's called ASCII, the American Standard Code for Information Interchange. And here it was, and we were in Clover. Now we can really go out and sell 501s. And guess what? We sold 100 installations in 2 years at $1 million a copy, which wasn't too bad for a small group. So we were off and flying, and now where do we go from here? What's the strategy? So Ted, you're no longer in programming. We have a guy who's a better executive than you are to run the group. I wasn't that good as an executive. We have a better guy to run that group. We want you to do some planning for us. We want you to become manager of a group called Product Requirements Planning. We want you to carry the banner for us into the future. Set the stage. What is it we need to build to survive? What is our strategy? Okay, well, they had already adopted a strategy of smaller and bigger. You know, we'll build a smaller version of the RCA 501, and we're going to call that the 301. Okay? We're going to build a larger version of the RCA 501, call that the 601. I don't know if the 601 ever got built. I forget, because by then I was long gone. But, And then finally, we're going to build a version of, an RCA version of the IBM 360, and we're going to call that the Spectre 70. Okay? Now, my group was doing studies. Well, while all this stuff was going on, we were studying stuff. We were looking at miniaturization, cost reduction, better price performance analyses, better price performance, smaller, cheaper, faster computers. This is exactly what we saw. And this was 1961, 62. Exactly what we saw. And we saw a company that built and sold large-scale or big-ticket consumer items. Remember, RCA was in the consumer business. They were selling television sets. They had an interest in Whirlpool wherein they were dealing with refrigerators and washers and dryers. And there was distribution networks set up for large consumer items, So my group came to the conclusion that maybe there's a market for computers in homes. In homes, 1962.
Wow. And this is before RCA became part of GE?
Yeah, they were still integral to RCA. They didn't become part of GE at first. They were sold to Univac. Became part of Sperry Rand first, and from Sperry they morphed into GE.
Remember where I had worked? They had Univac Series 70, Model 46.
Okay.
The first time they saw Univac, a guy showed up and slapped Univac Series 70 on the machine.
Okay. Okay. It was still RCA. We were still in a commanding position. We still had sold a couple $100 million worth of equipment in about 2 years for a very small part of that company. It wasn't too bad. And we were trying to plan the future. And my analysts and I came to the conclusion that RCA would be best served strategically by developing a home version of the computer. And the challenge came to me from the head of my department, who was an ex-IBMer. Yeah. You got it. He looked at that and he said, we're going to out IBM. We're going to be all things to all men. We're going to sell systems at all levels. This is what he said to me. And here's what I think of your strategic plan. Tore it up and threw it in the waste can. So what's the next thing that you do? What would you do?
Look for another job.
My resignation was on his desk the next morning. But the interesting part of that is that his boss came back to me and said, what would it do to keep you here? Do you want more money? Do you want a change of assignment? What would it do to keep you here? And I said, nothing. Can't do anything to keep me here. I'm out. And that's when I joined another ex-RCA person or two. We had like 4 of us. And we formed a consulting company, and I was out of that business. So we went on to bigger and better things from there. And where did RCA go? In a few years, their business fell off. The corporation decided to sell that division to Univac. And all of the RCA guys either moved to Univac or they were out of a job. We had people who cried and cried, we just moved to your facility in New England, just put a home, and I'm out of a job. Time marches on, people. It marches on. Nothing stays the same. That's the lesson. Let me see if there's anything I should have said and left out. Not really. I think I've come to the end of the remarks that I wanted to make to you. If there are any questions, I'd be happy to entertain those. Go ahead.
I remember working on the Spectre 7046, and I had previously begun as a programmer about 68. I was about 4 years of programming on IBM systems. And I really liked it. Well, we started with the TDOS, the tape disk operating system.
Okay.
And also I came on just about the time that the RCA announced that they were selling or closing their division, and immediately technical support vanished. And in a way that was lucky because we had our own inside technical people, but basically we were running TDOS, but I looked at the manuals and figured out VMOS really was a better use of system resources. And so I began, since nobody told me to do differently, I began writing my programs for VMOS and using that. And operations was evidently able to follow it. And I remember, well, they evidently after I left, they told me they had used my, I was the first one to set up VMOS, not that I was a genius, but they used them as examples there. But I remember an assembler manual realized later that the RCA assembler manual really wasn't an assembler because it didn't assemble into RCA code. It was the one for the IBM assembler. And the only difference is the RCA assembler manual was written more recently and therefore had better examples of coding. You know, it wasn't spaghetti code like the IBM manual, but assembler programs could have worked on either one. But I remember like the IBM job command language, the interface between the program and the system, actually was more understandable in RCA because I remember going into work one morning thinking of a problem and thinking, well, what kind of command would solve that? And I got to my manual, looked it up, and using the English words, I found the RCA command of the same name. And also, as opposed to the like straight line of the JCL.
I don't mean to interrupt, but you know, that's okay. I'd like to have this discussion with you privately, if that's okay. What I would like to, I need to make one more remark since you mentioned all this about the Spectra 70. The Spectra 70 caused us to rethink our image. We used to think of the RCA logo as the RCA peacock. When the Spectra 70 came out, lots of us said, we're not the RCA peacock, we're the RCA parrot. And that was very demeaning. And we kind of felt bad about that. So, you know, here went all this grand and glorious feeling that we had about the company. Yes?
I'm curious, when you designed the new instruction set
Yes.
for the new computer, did you keep the variable word length?
Yes, we did. Variable word length never went away. As a matter of fact, it still hasn't gone away, has it? That was pretty forward thinking, don't you think?
As far as I see,
We kept the variable word length, to answer your question specifically.
Yeah.
Yes. Absolutely.
And what was the advantage of that?
The advantages of it were that we did not have to waste storage. See, if you have a field that encompasses a word and a half, you'd have to dedicate 2 words to it, don't you?
Yeah.
In our view, we didn't want to do that. So the storage requirement was just as long as the field was. We used one symbol to designate the beginning and the end of the field.
Did the processor have registers?
Yep, had registers. The processor was designed to have a CPU with an arithmetic unit and a logic controller. It had memory registers for data going in and out of the core, in and out of RAM. Memory address registers to handle addressing for the RAM. It had a register for the program, and this is what we used when we wanted to switch locations as to where we were in the program. Just simply change the contents of the program register with a go-to, you know, or a conditional transfer of control. We'd go to here if this and if that, go to somewhere else, and okay, if the same, go straight ahead. And all we did was substitute an address for the contents of into the program register. We used buffers, of course, for all the peripherals, and a bus to connect everything up, just pretty much like the way it is now.
Is this the 501?
501? Yeah, this is 501. We're talking about the 501. Oh, absolutely. Yep.
The Bizmac that was like ridiculously huge physically, how long could it run before you had to replace parts?
That's a really good question. Maintenance of the 501 was one of the nightmares. I actually had a conversation with one of the engineers on the Bizmac, and he said that you're never going to get reliable operation for a full shift. And he based his analysis on the number of parts there were and the average failure rate for each type of part. It was a very, very large number of components, and the average failure rate on some of these vacuum tube elements was fairly short. So his theory was you can't make the Bizmac work. You know, it's just like saying, you know, the wings on a bee won't let it fly, but it flies, and it did fly. But his analysis was perfect. It just didn't represent reality, that's all. So, you know, it was a maintenance nightmare. But the good part is we could find a guilty circuit, pull the board, change the element, and put the circuit back in. you know, the diagnostics were pretty good. And they had to be good in order for us to keep going. We had engineers on roller skates. You know, maintenance engineers on roller skates. They were using computer-generated speech just to hear the system tell them what to do and where to go. They had automated wiring diagrams, so that if you had a pin connection here, it would tell you where the other end would be. That kind of stuff. Oh yeah, that had to be in order for it to work. So yeah, that was a really good question. Yeah.
That Bizmac system, do you use any sort of marginal checking to predict failure points?
No, the only checking that I really knew, maybe it did. I'm not that much of an engineer. We had parity check. Every character had an extra bit, you know. We used odd parity. I don't know, they still use odd parity? What do you think, guys?
Well, ECC isn't really parity.
Who uses odd parity? Who said we
But
did?
the original PC used parity. I don't know whether it was odd or even.
Well, the reason we used odd parity was so that we could distinguish all zeros from absence of a signal, and we had an extra character for free. That's why we used it that way. Okay, any other questions? Yes.
Got a question. Would you say that the executive command language, the equivalent of the JCL, was more like either Unix or what was the other, virtual machine? In other words, you could branch logic and do all sorts of things within the
Well,
executive
JCL,
command
job
language.
control language, was really not one of the issues when I was there.
Oh, okay.
That stuff came up sort of a little bit after me,
Yeah.
and so I really can't answer your question.
Okay.
I know I used JCL. I mean, I did myself later on other systems. I know what you're talking about.
Well, I think
Yep.
I heard a rumor that in the older computers, if you weren't careful and you gave it a wrong series of instructions, you could make the machine catch fire. Because there would be too much current flowing through one of the circuits. Is that just a myth?
I think so. I never heard of it. I never saw it happen. I know, and here's what I do believe. I believe that if you enraged our operator enough, his glare would start the machine on fire. But you see, here's one I didn't tell you. In my view and in my experience, machines have personalities. The old Bizmac prototype was a female, and she fell in love with our chief operator. When he was in the room, everything worked. When he left, it stopped working. As soon as he came back, it started to work again. So we figured there was a love affair going on between he and the machinery. I don't know why, I don't know how. It's just observation and one of these silly notions that you get in your head. So, you know, it's just as logical as the other. Any other questions?
I have a-
Yes. Yes.
Do any of these machines still exist, or are they, where would you go find one?
You won't find any Bizmacs still in existence. You may find a 501 somewhere. Don't ask me where. We delivered about 200 of those, or 100 of them. I think they've probably all been replaced. Don't know. I really don't know. I haven't tried to track it. I don't know. So I can't answer your question. Except with an I don't know. Yes?
I remember in high school, I was like reading through a music history book, and I saw a picture of like a huge computer, and I read it was like RCA Mark II synthesizer from like the 50s, I guess, or something.
Synthesizer.
Yeah, it was something like that. I don't know.
You mean a Moog synthesizer?
No, this is before it. It was, I guess, installed in Columbia, Princeton. I was wondering if you knew anything about it.
No, I don't know anything about that.
It was like some kind of punch card machine of some sort.
You know, I teach at the business school at Rutgers University. My students, most of them, never even seen a punch card. Have you seen a punch card?
We'll sell you one for
Not personally.
What'd you say? Not personally, right?
I mean, I've seen
Okay. Okay, anything else? Yes.
You stated that COBOL solved the software portability. How well did that actually work in practice back then?
Actually, not too bad, really. See, it took a little while for everybody to develop a COBOL compiler. COBOL was a product, it was a software product that stayed active for about 45 years, maybe 50 years in the field, still used. And what they did was they upgraded COBOL with newer and newer versions that were all compatible upward. Not downward, but all compatible upward. The older versions would work on the newer versions. And they streamlined COBOL. Let me tell you a few things about COBOL. You probably know, if you know COBOL at all, that the COBOL programs were divided into divisions. There was an environment division, there was a procedures division, and there's a data division. In the data division, every COBOL program needed to have a descriptor for each file that was used in that program. That is, if you know anything at all about Access these days, you know about Microsoft Access. If you use Microsoft Access and you design a record, okay, you get a design view of the record, and the design view of the record is what you needed to have in the COBOL program. You needed to define every field and its properties embedded in the program. And so a later version of that said, no, we're going to take all of this stuff, store it up in a database, and just give it a name. And so when we write the COBOL programs, we'll just access that definition by cross-referencing the name in the COBOL program with the definition up in the database. So you didn't have to sit there and write each field and describe it. And every time, and if that same file was used in multiple programs, you'd have to redefine it and embed it in every program. But now we have a data dictionary, and just simply reference the data dictionary in the COBOL program in the data division. You don't have to do that anymore. Now you can maintain that record. You can change the fields and stuff, and it'll impact all of the programs simultaneously. Any questions? Any more questions? Yes?
Your control function, you obviously must have had some control function. Even to begin a program, you need something, a boot program. So how did...
Oh yeah, by then we had operating
systems. Since you were programming, how did your programs grow from a boot, your control function from a boot program?
Okay.
How close did they get to operating?
I guess I forgot to mention this. The 501 had a full-scale operating system. So when you booted the system up, there was an automatic boot, what we now call BIOS. It's embedded on a piece of core memory in a non-addressable portion. And when you invoked it, it would bring up the operating system, and you can then invoke from there. But it was done by menus, pretty much the way it is now with Unix and Linux. We did not have icons. That didn't come along until Apple invented that notion later on.
Actually, that was Xerox.
Or maybe it was Xerox, I forget. Apple was the first one that was extended.
It was around for a while before Xerox implemented it. They were the first to do it.
Okay, but Apple first came out with, they first came out with the mouse too, didn't they? And it wasn't called the mouse, it was called the Lisa.
Well, Lisa was the system, was the computer that
Pointer,
used the mouse, but the Xerox made machines with mice before.
Yeah, okay, I stand corrected.
Okay.
Okay, anything else? Ladies and gentlemen, thank you for your attention.